Hey there, kids, sick or just away because of the cold weather. I'm just going to go through today's pretest I did yesterday, actually, and get you prepared for this test that's coming on Monday. Hopefully, you'll study over the weekend. And also, there'll be another video which we discuss a couple additional questions about intensity. And that video will be attached to another document that's also going to be on Google Classroom as well. So maybe you want to open both those up, the pretest and that other document, and follow along. All right, let's get started here. So, so question one, a source of an electromagnetic radiation, EMR, operates at a frequency of 95.2, sonic 102.9, or 106.9 Verge radio. Those numbers actually represent the frequency in megahertz of that radio station. So when I see a megahertz, because of my worldly experience, and when I see megahertz, I automatically jump to that's a radio station. Like frequencies that's in the gigahertz, like 2.4 gigahertz or 5 gigahertz, like the stuff where your Wi-Fi works, that's actually microwave radiation. So use the microwave transmitter for that. So if you ever use your laptop close to a microwave and it's in the way of your router and you're using Wi-Fi at that time, you might notice that when you turn the microwave on, it interrupts your signal, and whoever's using the laptop can't use the Wi-Fi. So microwaves and Wi-Fi run on the same thing, microwaves. And the radio stations, they're all megahertz, right? So I know for sure right now that this is going to be a radio wave just because of that megahertz piece right there. So I'm just going to cross off these microwave answers. Now my only two options here that I have to figure out is actually how many photons that's going to be. So the first thing you're going to probably want to do is figure out what is the energy of this photon, right? Let's see if that's actually working. Yeah, it looks like it is. So we're going to go H times F because we do have a frequency. And because of the units of a watt, and a watt is a joule per second, so remember that's how you find power, work divided by time. This is a joule here, and this is a second. I can use that knowledge that this has to be a joule to figure out what H value to use. So I'm going to use the 6.63 times 10 to the negative 34 joule second version of this number, and I'm going to type in this one as well, right? Megahertz. So, but the mega, I'm going to make sure that times 10 to the 6. I'm going to get rid of that prefix. Really, the only thing that should have prefixes are kilograms in physics. And while you guys try to figure out what that number is, oh, never mind. I thought I had to go pretty far. I just had to find my key. Right? Oh, my tooth disappeared on me. Every time I look this way, I'm just kind of looking at my picture in the bottom corner of my screen on my other monitor here. I'll just drop here. Okay. So once I type those two things in, I'm going to get an answer of 6.31176 times 10 to the negative 26 joules. An extremely small amount. Like remember our formula, which we're going to discuss on the next question. Because the frequency is really low compared to all those times 10 to the 15 terahertz and all that other stuff. We're going to have low energy, right? The lower the frequency, the lower the energy. So this is a really, really small energy here. So what I'm going to do is I'm going to use that to determine, actually, I'm not going to use that yet. I'm going to first of all determine how much energy this is actually outputting each second. So I see this per second here. So that means the time is 1 second. So using this formula up here, I can determine how much work is being done by going power times time. So power times 1. So that's just 100,000 watts times 1 second. That's just 100,000 joules. I'm looking at this number. This is a huge amount of energy compared to this number here, right? But if all we're doing is outputting just tiny photons, how am I ever going to get this number? Well, it means I have to have a lot of photons, because a lot of photons are eventually going to add up to this number. So I got to figure out how many of these fit into this number down here. I'm going to do a little You can cross multiply divide. You can do lots of different things here. So here I'm actually going to do a cross multiply divide. I'm going to say that one photon, that's this top number here, 6.11, corresponds to this number of joules. Okay. How many photons correspond to the 100,000 joules that we're trying to reach here? So we're just going to cross multiply, divide, and we're going to get an n value, a really big n value for this one, of 1.58. Well, I could stop there, but let's keep on going. Times 10 to the 30 photons. Photons. Okay. I'll look at this, and that's the answer right there, so it must be B. We did a few of those questions in our notes. We're also going to do a kind of additional similar question in our extra practice questions later on. Okay. I was talking about this before. This is an extremely small amount of energy, smaller than most of the energies we've seen so far, because of this frequency and energy are related to each other. So if I know that frequency and energy are related to each other, the smaller the frequency, the smaller the energy. Most I'm thinking, oh man, I don't remember the waves based on frequency. I remember them based on wavelengths, or the spectrum based on wavelengths. So the other formula, hc over lambda, says the exact opposite. It says that if my wavelength goes down, my energy goes up. So the things with the smallest wavelength will have the highest energy, and the things with the longest wavelengths will have the lowest energy. Now, if I look at the radio waves up here, this radio wave, if you actually convert it, some people actually did that in their thing, you get like 3.2 meters or so. That's huge. So that's a pretty large wavelength. So that's going to be a pretty low energy. So radio waves actually have the lowest energy, so that's a 1. Then if I keep going down the list, just remembering the order that I told you guys to try to remember this whole time, it's going to go radio, it's going to go microwave, it's going to go infrared, right? But infrared's not on our list. Then it's going to jump from infrared into visible, and then it's going to go ultraviolet, then X-rays, and then gamma being your highest. If there were cosmic rays in there, they'd be higher than that, but in this case, gamma is your highest. Okay. There's 2 marks. There's 3 things here, like 3 marks, or 3 things give you a mark. You messed up 2 of them, then lost a mark. Okay. All right, so this next one, well, I got this thing on my bottom of the screen. You probably don't want that beside this. There we go. So on this next one here, we're just trying to figure out which of these wavelengths have been released by the sun, right? There's lots of wavelengths, but they've only given us 4 of the wavelengths being released by the sun. Which of them has enough energy to overcome the work function in the photoelectric effect? So whenever I see the word work function, I think the photoelectric effect. Right? That's not photoelectric. Photoelectric effect. So how the photoelectric effect works is the energy in from the photon is going to strike an electron. The electron is going to take some of the energy, try to dig itself out. That's a W. And if it has any other additional energy out, off it goes in the form of kinetic energy. What we know is that these 2 things here add up to these things over here. But the goal is to cause the photoelectric effect. This energy, the energy of the photon, which is write that down, the energy of the photon, photon here, has to exceed the work function. If there's not enough to get out here, but like if I stop halfway, it's not going to do anything. It's just going to bounce off and off it goes. So this photon has to exceed this minimum energy here, which is the work function, exceed this energy. So there's a couple of ways to do this question. You could just find all the energies of all these photons by using hc over lambda, and you could do this 4 different times. Actually, probably just do it 2 times or 3 times before you stop, because eventually you'll reach the answer you need to get. But rather than doing this 4 different times or 3 times or so, what I did instead was to convert this number into a wavelength. So I use that same formula there. I convert it. So I turned it upside down. Oh, I should look I got my key here, so I'm just going to look at my key. So rather than typing it all brand new,
I'm using this formula here, so I'm not going to do this up here. By the numbers there, we're going to go 2.34 times 10 to the negative 7 meters. So that kind of matches these. We've got -7, -7. So these are all in like nanometers. Okay, so now we're using our knowledge that we just from the previous question here, that energy is inversely proportional to wavelengths. If I have a lower wavelength, so these are smaller wavelengths than this one here, that means these will have more energy than this number over here, because it's smaller than this wavelength. And if my wavelength is larger, it means this will have less energy than this number over here, this 1.5 number, or 8.5 number. The goal is to have more energy, because I want this photon energy to have more than a W. So which of these photons up here have more energy than a W? Well, the ones that have the lower wavelengths, so 1 and 2. This is really close, but it's enough. It has to be just enough to get it outside the metal, and then off it goes, whatever's left over. So it's going to be 1 and 2 in this point. Okay. Next one here. So the next couple, like 4 and 5, are going to use this knowledge of this picture right here. The energy of the photon has to equal the energy of that electron that comes out. Okay? Conservation of energy, which I have like a thing. Conservation of energy. No? Okay. So, I need like a little box, like a sound box for myself. So in this investigation, you got the photoelectric effect, you got this photon of some energy, we got another work function here. So what I know, actually, let's keep on going. The student recording, we want to find the stopping voltage. We want to determine the maximum stopping voltage. We're looking for V stop here. So to determine V stop, I'm going to write it way over here because I know there's going to be more work over here. To determine my V stop, I need a few different things. One I already have. It's a photoelectron. It's always in the photo cathode or the photo experiment. It's always going to be an electron anyway. So we know the charge of electron, but to find the V stop, I need my EK. So I'm going to go V stop is equal to EK divided by Q. Okay? So that's what I need to figure out. So on this side over here, I'm going to write down what we have. So what do we have? We got the work function, which is 1.90 electron volts. And I got the frequency of the photon, 5.17 times 10 to the 14 hertz. Okay. Using this up here, I can see there's an EK in this picture, right? Up here, there's an EK. It has this photon, it's got this W. Using that information and the conservation of energy, the energy of the photon that's going to go in has to go somewhere, because remember, it's an all or nothing. Also, it's one photon for one electron. We'll talk about that later. That photon is going to get absorbed by the electron. If it can, if it can't, then the electron just bounces off and it reflects away. So maybe this one can. It looks like maybe it can. We'll have to double check the energy of this photon. But if it does get absorbed, it's going to be used to dig itself out, and then whatever's left over is going to be EK. So conservation of energy right here. What goes in has to equal what comes out. The photon energy, the electron's energy over here. I'm looking for that EK electron, so I'm just going to subtract this number over. Photon minus the W. Okay, so we know the W already, so that's 1.9 electron volts. To find this photon energy, I'm going to go to HF because I have the frequency. I'm going to use the H, the electron volt version of the H. Okay, so the 4.14 number. I'm going to get 2.14038 minus 1.9 again. And we get 24038 electron volts. Okay. So it's a positive number, so that's good. It means the photoelectric effect took place. Like you can see, this photon has more than enough energy. This number is bigger than the work function. So I dug it out, and whatever left over is going to be my kinetic energy. What happened now,
Because a lot of you just took this number and just plopped it in here, did the calculations, and then you got your V-stop. But that's wrong. Something else has to happen in between these two steps. Most of the math, most of the formulas you're going to use, if they don't have an H in it to help you with the conversion between joules and electron volts, then you're going to have to use the joule version of the number. This electron volt is going to have to be converted first before I go too far. So I'm going to change this to joules. So knowing that 1 electron volt is 1.6 times 10 to the negative 19 joules, I can use that to figure out how many joules this is. So you just have to multiply the two numbers together. So this is a fraction of electron volts. I'm going to get a fraction of this number here. So this turns into 3.846 times 10 to the negative 20 joule. Now I have this number. Now I can plop it into that spot there. Okay, so this way's wrong. This one's right. Okay. So I'm going to take this V stop. I'm going to take this number here, divide it by Q, and then get that exact same number out. But the different unit. So here it's electron volt, so this means energy, and here it's a potential difference. Now it ends up being the same because really it's just multiplying by 1.6 times 10 to the negative 19. And then up here, you're just dividing by the same number, but it's a different unit. This one's in joules, and this number here, when you use it, is 1.6 times 10 to the negative 19 coulombs. They just happen to have the same number. One's in joules, one's in coulombs. So you get you essentially get that same number out that you start off over here. This 0.24 number, now you get over here. But that's a more reasonable number. So if you didn't do that conversion, you're going to get this huge voltage, and voltages are never that big. Maybe in the hundreds or maybe thousands. Maybe you get like 100,000 or something, 10 to the 10. That's just too big. You wouldn't want to be in the same room as that device or apparatus. It'd be awesome. It'd be like electrons just coming out. It's beta radiation, so it's pretty dangerous, probably. Yeah, so let's not do that. The next question is very similar to question 4. You need to find that EK because you want to find that maximum speed. So to find out the EK, or to find the maximum speed, we're going to have to use the EK formula, 1/2 mv squared. Just rearrange this, times it by 2. Divide by the m and take the square root. So I need to find that EK first. So we're going to use that same knowledge here. So we've got E photon is equal to W plus what? What am I doing again? Plus the EK. Hey there. Yeah. So what are we going to do here? Oh yeah, so we're going to subtract over the W. Find that EK like we did last time. Photon minus the W. Photon, you can just go HF because we're given a frequency of the photon here. Minus HF naught. You can see this is a threshold frequency. That's your F naught. So there's enough energy here to get over this. You can remember frequency and energy are directly proportional. This has more energy than this one. So the photoelectric effect is going to take place. I'll plug all these numbers in. And we get 1.7238 times 10 to the negative 19 joules. Okay. Once you have that number, plug it in. And you notice that the units of this are already in joules, so we don't have to convert them. Right? I use the H, I had the joules, I know that the EK formula, 1/2 mv squared, has always been joules since science 10. I'm going to make sure the units are correct here. Then my speed here is going to be reasonably fast, 6.15 times 10 to the 5 meters per second. There you go. So 615,000 meters per second. Okay. So question 7 would be easier if you actually did the next questions first, because it talks about Compton and de Broglie. Down here, question 7, or sorry, 6, sorry. Question 7, it talks about how moving particles behave as waves. And then down here, Compton saying that things with wavelengths behave as if they're particles because they have momentum. So waves have momentum, and things with momentum behave as if they're waves. So we put those together. So I write this down, the wave nature of matter, the wave nature of matter, that's de Broglie, right? De Broglie, if you want to say it that way. The particle nature of light, that's Compton. But if I put these together, I get the wave particle duality. Sorry, it's fancy Friday, so I was wearing fancy shoes, and they are very uncomfortable. Chuck those off on the side there. Okay. Yeah, so we got this kind of duality here. So waves behave as matter, and matter behaves as waves, and just goes back and forth, and we get this wave particle duality. All right, moving down to this next one here. De Broglie hypothesized that these moving particles, things with momentum, behave as waves. So they give us this nice little formula. It's just a rearranged version of this formula. We just rearranged it. So if I have momentum, I'll behave as a wave. So everything that has momentum will behave as a wave, maybe not noticeably, but the faster you go, or the smaller that momentum, the more noticeable your wave is. You can see it's inversely proportional. So if my momentum goes down, or sorry, if my momentum, yeah, so my momentum goes down, I could have a more noticeable wavelength here. Or if I go the vice versa, up and then down, right? They're inversely, it doesn't really matter too much. But I can find the momentum of a moving particle by going mass times velocity. So because it's an electron, I'm going to use the mass of an electron. I know how fast it's going, so don't try to mix this up with the speed of light. So you can't use this formula. People are trying to use that one. And you can't really, because this requires that you move at the speed of light. And things with mass cannot move at the speed of light. Massless particles, like photons, yeah, they can. So you can use that formula with a photon, but not with an electron. But this one, you see, it has a speed and it has a mass. So I just plug those two numbers in. I can actually write this out if you want to. 1.99, 9.11, sorry, what was I saying? Times the 4 times 10 to the 5. I punch those all into my calculator. I get this number. Kilogram meter per second. Pretty small momentum. But that's okay. We have a nice small momentum. What I'm going to do is now plug it into this formula up here, H over P, making sure because P and wavelengths, it doesn't really matter. But this formula just need to use the Joule version of this thing. So the only way it actually works out nicely. Put your two numbers in. Don't really have to write all of this out, I guess, but put them in. You're going to get a nice number here, 1.8 times 10 to the negative 9. I want 2 sig digs because there are 2 sig digs in this question here. But also, hey, look, we got times 10 to the negative 9. We know that's a nano. So I can do that. So you just divide by 10 to the negative 9 here. You realize that you just get 1.8 nanometers. Pretty small wavelength, right? So lots of energy here. Small wavelength. Now, some people got a little messed up in the conversion here. So, because it doesn't specify up here what the wavelength should be expressed as, it's your choice. But if you try to change between the units and you make a mistake, I'll dock you marks, right? So, if you're not really comfortable with converting between units, or you think I could make a mistake, just stick with this answer here, put a box around it, and then you're happy, right? Don't try to do conversion unless you have to, unless I specify change it to nanometers. If I don't specify, just leave it in meters. If you want to change it to nanometers, go for it. Thumbs up. I'm happy with that. Happy face. Maybe you'll get a sparkly sticker. Right? Maybe. I haven't decided what's sticker worthy here yet. Let's go down here. Let's see what else we have here. Oh yeah, so that's that. Happy. Got my wavelength. Next question. We got Compton coming along. It hits an electron. Now, what I know about this formula is that we did, at one point, if I search it again, is I think the wiki, the component effect here. It's kind of, I spelled it wrong, but I don't want to do that. Ah, here we go, component scan. So I did this before. I showed this up to you. I probably should cancel this out. Go away. Okay. When it comes down here, the derivation. So here's the derivation, description of the formula, derivation. Part of the derivation, I showed it to you at the top, is that it has to take into account these two things. Conservation of energy. So the energy before is equal to the energy after, and conservation of momentum, right? Or the momentum before and after. So we looked at those two things. We said those two things have to be taken into account. And then all the way down here. You can actually see that good. All the way down here. It takes a lot of work, a lot of work, a lot of work. Oh, and here's the formula. The change in the wavelengths is equal to this stuff here. Right? So the two things you have to take into account when you're making that formula: the conservation of energy and the conservation of momentum. Because the energy's got to go somewhere. You can't release it as heat in this situation because there's all this empty space. And heat is just the vibration of molecules. And there's no molecules to vibrate because it's all empty space. And there's no heat. Heat is vibration of molecules. So vibration of molecules such as that free electron. So he gets the heat in terms of kinetic energy, but he gets the energy from the photon, right? Can't get energy from nothing. So the photon gives it the energy. And same thing with the momentum. He has momentum afterwards, so the momentum had to come from something. So it came from the photon as well. Ooh, excuse me. I don't know if you can hear that. All right, well, I could. Let's see what we have down here. Oh, we need to find the final momentum of this photon here. So we're looking for P final. We have a P initial here. I'm not too concerned about that, but we have an initial wavelength. But to find this final momentum, I'm going to need the final wavelength, right? Because the wavelength is going to change if I give energy to the electron. If I lose energy, my wavelength goes up. So if my wavelength goes up, my momentum goes down. Awesome. Also, it's going backwards. We're not worried about that too much. So the magnitude of this final momentum, I need to find out what this final wavelength is. So I've got to use this change wavelength formula to do this. But before I do that, I got to figure out a few things. Like the H here, okay, that's going to be the joule version. The M is whatever it hit. Oops, it hit an electron, so this would be a mass of electron here. The C is if you'd like. Okay. Now this is the tricky part. What's this angle? A lot of people put down 0. The problem with 0, if I did use 0, then my wavelength doesn't change. But my wavelength has to change. What 0 means is that the wave, when I hit it, the scattered photon just travels straight on through. That's 0 degrees from the initial direction. So here's the initial direction, here's the new direction, there's 0 degrees between them. But what we know is that it's going forwards and then all the way around the other side. So there's 180 degrees difference there. So it was going this way, but now it's going this way. There's 180 degrees difference there. That's the maximum change. We're going to use that theta of 180 to solve this question. Okay, so I can find the change. Let's find the change first. I go 1 minus cos 180. Plugging it all into the formula. I think I should get the right page. All right. Yeah. This number's familiar because we've done this one. It's actually in our notes. But this is the maximum change of any photon. Because nowhere in here does it say what the initial photon had to be. This is just the change of anything that's colliding at 180 degrees, so scatters backwards at 180 degrees. Okay, so it's a relatively small number. But in terms of the initial wavelength that's right here, this is the nanometers. Let me just write that down. Initial meter is 0.13 times 10 to the negative 9 meters. They're actually relatively close to each other. They're actually, if I were to put this in the kind of the same exponent, move it over a couple places, it'd be like starting right here. And you'll see that when you start adding them together, because if I go change is equal to final minus initial, add over the initial here. I can get that final wavelength to be, if you were to like move around the decimals and stuff, 0.134851811 times 10 to the negative 9. Nope, 9. Now, the calculator's not going to do that. It's going to be negative 10. It's going to move the decimal place over for you. But this is what it would look like. So there's your new part of the number that's changed. It went up, which is good. And this is the old part here, right? That's my initial folder. So I just tacked this little piece on here. So what I knew is that the initial momentum is h over lambda. This ends up being about 5.1 times 10 to the negative 24. But because of this tiny little increase of wavelength, my momentum is actually going to be 4.92 times 10 to the negative 24 kilogram meter per second. So my momentum's gone down. Right? I don't know. There you go. How did I find that out? Oh, yeah, I didn't write my formula down. Oh, I just used this formula here. This was using the initial, but for this one, I would use the final, which is using that number there. Okay, the next couple of questions here talk about history and theory. So one immediate result of the discovery of the cathode ray particle was the theory that the theory of the atom was revised to a theory that hypothesized. And this is using that picture there, right? So let's see a good picture. That's a cathode ray. What did that discover for Mr. J.J. Thomson? So J.J. Thomson, yeah, this is J.J. Thomson, because he was the one that was doing this. So this discovered that the fact that the atom is not indivisible. That was Dalton. The cathode ray wasn't around at that point. Maybe it was, but they weren't doing experiments. So it's not going to be that, right? Dalton thought it was indivisible. It couldn't describe this cathode ray, these negative particles coming out of it. That was going to be J.J. Thomson. So I'm going to jump down to here. It says an atom contains these negatively charged particles. It gives you that plum pudding model. These other ones here, this is like De Broglie. This one here is Rutherford. This is called capital. Okay. So those ones that done with the gold foil experiments or just general knowledge and theories and stuff. We come to this point. The bottom, we can go back up. Okay, so we come to this point here. To get to this, so these are the three models here. We got the plum pudding model, we got Rutherford's model, we got Bohr's model. To get to the plum pudding model, we use cathode rays. Okay, that's what they used to get to this point. Okay. So I can't use it to get to the next model. So obviously it's going to have to be the scattering of alpha particles. Now that's key later on. Alpha particles, positively charged particles. Okay. So we use those alpha particles to decide that the nucleus had to be something, well, all the positive part of it and most of the mass is somewhere in that tiny infinitesimal little dot in the middle, and these electrons are whizzing around it. Right? But that model had a couple problems. Couldn't explain three things, right? One of them is not described here. The one is the periodic table, right? Couldn't explain that thing. Like, why does it repeat and why do certain elements act the same way? But the other two things it couldn't explain either. One phenomenon, that's this piece in the middle that I couldn't explain, was the emission spectrum, the bright line spectrums, or even the absorption spectrums, right? We haven't talked about radioactive decay. Compton scattering has nothing to do with atomic models. It just has something to do with the wave nature of the electron, or sorry, the particle nature of photons that leads up to the discovery of photons and stuff. And another thing that it couldn't explain why things didn't release electromagnetic radiation when they were accelerating around. They're always accelerating. So they had to modify the theory to the Bohr model here, right? So this is the Bohr model. This is going to be the nuclear model. And this is the plum pudding, right? Remember, before that would be the billiard ball. Cool. So 136 going across. Only one answer. These other guys here, they didn't really do too much for this. All right, so parts of J.J. Thomson's experiment that he was using for the cathode ray, there's 3 parts. You have the, again. So at the beginning, right over here somewhere, I'll put the camera in the right spot. I'll start making you guys all dizzy. So at the beginning there's the accelerator that accelerates the beam up to a certain speed. Then in the middle somewhere, right about there, is the speed selector. If you're going too slow, you go up or down. If you go too fast, you go up or down. But if you go just the right speed, you go straight on through. And then the last little piece right over here bends the electron over a circular motion. And you can use that to calculate the charge to mass ratio. That was the whole point. Find the charge to mass ratio. It's technically how a mass spectrometer works. What's the charge to mass ratio? And it can tell you what compound it is. So the second part, the undeflected part, the keyword is it's undeflected, right? So it's coming along and it's going too slow, it goes up, it's going too fast. But if it's going straight through, it means that if I'm undeflected, I'm going to have 2 forces here. One force caused by the electric field, which they give you, is 150,000 joules. So you do have to watch out for these. That's times 3 there. And one force is caused by the magnetic field. Hopefully they're perpendicular to each other, otherwise it doesn't work. But these 2 forces have to balance each other out. The fields don't, but the forces do. So to find the force, we'll use E times Q for that side and Q for this side. Cross off the Q's, rearrange for V. And there we go. So plug your 2 numbers in, 150,000 Newton per Coulomb, and 0.160 Teslas. All right, what do we do? Flip it over twice. We think it's something big, like 900,000 here. So 938,000 meters per second. Okay. Once you have that speed, you can use it in the next question. I know there's a little typo here. This should say 12. It's just, I was moving questions around. I've got to change that. But if you didn't find that speed, you could also use this. So you can see they're relatively close. This one's a little bit faster. This one's a little bit slower, but they're pretty close. So again, it gives you a hint that you got something right. Now this is usually going to be a pretty big speed. So if you get like 9,000 or 900, even 90,000, that's getting a little bit slow, but maybe not too bad. If you're 9,900 or 90 or 9, those are slow. So this part of the experiment is a fast speed. If you're going too slow, gravity is going to have a pretty good effect on you. So in the next one here, it's going to go into the third part that's going to be bent by the magnetic field. So the force is not actually balanced out. There's only one force. What is that force? Well, a lot of people say it's the centripetal force, but it's not. The centripetal force is not a force. It's the net force, which means it is the sum of all the other forces. So if I have this thing going one direction, there's only one force acting inwards. That's my magnetic force. It might be gravity. Let me draw gravity for you. There we go. I just drew gravity. It's this tiny little piece here. If I were to draw gravity, look at this tiny little thing. It's going to be so small you kind of ignore it. But if I add those all together, I get a net. And because they're acting towards a circle, we call it an FC rather than F net. So you can go F Q times B here, or QVB. And FC is just a net, so it's M times A, but M times AC, because it's circular. And so it's A, in this case, is V squared over R. It just makes it, you don't want to use the other one. We'll cross off something here to make our lives just a little bit easier. And then our rearranging, you have to watch out. Because the R is in the denominator, I shouldn't just start moving things away from it. First of all, I want to move the R so it's in the numerator. So I'm going to times it up to the other side. So I get R times Q B times M times V. Now it's in the numerator. That's good. I'm happy. It's happy, right? It doesn't like being down here. It wants to be on the numerator. Then I could start moving things around, right? So I can divide the Q down, I can divide the B down. I get this formula. If it's upside down, you're going to get some weird number. So plugging all the numbers in, making sure you use the proper B value here. This is going to use the 2.2 times 10 to the negative 3 Teslas. That's here, not this one here. So I'm going to use it for the third part. So there's different Teslas here. It's also a milli. That's times 10 to the negative 3, right? So we got the Teslas here. We got the charge of an electron that we're allowed to use. We can use the speed here or the one above it. If you trust the one above it, I do. And the mass of an electron. So plug all that in, and you get 2.43 times 10 to the negative 3. And if you trust your conversion, this is going to be 2.43 millimeters. That's what a milli is. Look at your chart. Negative 3. If you ever see like a multiple of 3, like 3, 6, 9, etc., 12, 15, then it's probably going to be a prefix attached to it. Centimeter, decameters, those guys are unique. And most of the time, it's a multiple of 3. That's good. Okay, the next one, very similar to like 2 questions back, you've got this thing that's suspended or moving at a constant velocity or moving in a straight line. It means that there must be forces being balanced out here. We've got a relatively large, I know it's negative 14, but it's large compared to like that electron, negative 31. But there's relatively large mass, and we got an electric field. So we must have 2 forces, and the 2 forces are going to be gravity and the electric field kind of balancing each other out. One's going up, one's going down. Right, so that they always balance each other out. They're just going to add to 0, so that means the magnitude of these numbers are the same, but the signs are going to be different. But I'm not going to be concerned about the sign being different. I'm just worried about the magnitude here. To calculate gravity, go mass times gravity. Calculate this one, go E times Q. Just watch how you draw your Q's and your G's. They might look the same. Let's find that Q there. So I'm just going to leave the Q alone because it's already in the numerator. That's good. Just leave it there. Divide the E down and flip over your key, and you get 3.23 times 10 to the negative 19. Cool. Now there are 2 sig digs here, so if this was your answer, I would leave it as 2 sig digs. Right? But this is not what my answer should be. My answer is how many electrons are going to be on this oil droplet. If I ignore the times 10 to the negative 19 because that's what an elementary charge is, this number is approximately 2 times that number. But if you want to, you could just divide by this number here. What elementary charge is, that's the coulombs per electron. Okay. And you can see that you're going to get approximately 2. Just 2. It's a whole number. You're not going to get 2.0 electrons. You're just going to get 2 electrons. I know the sig digs up here are 2 sig digs, but you don't put 0.0 on whole numbers. A whole number of electrons. You can't have like a fraction of electrons. Don't put a decimal there. Right? Round it to the nearest one. Now, there was a question in class like, what if you got like 2.5? What do you do there? You've got a 2.5 or 2.6 or 2.4 or something. If it's not close to a whole number, go back and look at your math again. Maybe you typed the number in wrong. It's got to be like 2.9 or 2.1, right? When you're getting close to whole numbers, that's good. Just round them up or round them down to the whole number. But if you're halfway between 2 whole numbers, recheck your math. Like, something must have been typed in wrong, right? Double check your rearranging. Also, these are never really that big. If you're like in the 500 electrons, then something's a little bit off there. Okay, so the next part. Now, before I do question 15, I'm going to look at question 16 here, because question 16 has numbers over here. Right? They have the numbers. So these numbers correspond to the energy levels, but look at the numbers. These are the negative, they're negatives, like this one's also negative here. Right? So if they're using negative numbers, as you go up, the energy should increase. And they do, because you're less negative means you have more energy, right? The bigger the negative number, the less energy. Think about the number line, right? Here's 0, If I go this way in the negative line, that's less. So negative 10 is less than negative 2, right? So these guys are actually bigger than these ones down here. Okay? Make sense? Even though the numbers look smaller, they are actually bigger because of the number line, right? But look at the numbers too. So negative 90, this is negative 20. So it actually kind of has a smaller magnitude to it. But looking at this number, that's what we're trying to find. What I know it's going to be somewhere like maybe negative 4 electron volts, negative 3 electron volts, negative 2 electron volts, negative 1 electron volts, 0 electron, probably not 0. 0 is the ionization level. It's not going to go positive. It's always going to be negative if we start off with negative here. So 0 is like your upper limit here. That's your N infinity. That's where it ionizes. The electron flies away. It's gone. Right. So we got to figure out what that number is. It's going to be somewhere in that kind of range there. Maybe some decimals there. So we're going to use this photon here to figure that out. I'm going to, first of all, I'm going to find out what the energy of this photon is. That's going to be useful. It's always useful to find the energies if you have wavelengths and stuff. This ends up being 2.1086 the electron volts. I picked electron volts because that's electron volts. I want to make them match. Okay. So now the next question is, where does this energy come from? Well, it's got to come from somewhere, right? Conservation of energy. If the energy, if the photon all of a sudden has energy, because the photon is just pure energy, no mass, it came from somewhere, right? And it came from this electron transitioning down, right? So it moved down levels. It didn't move, it just disappeared and reappeared. But as it did that, the electron lost energy and the photon got the energy. Conservation. The electron loses energy, photon gains it. It could go the other way too. The photon is lost, the electron gains it, right? So I need to find out what this is. Well, I know what it is, because the conservation of energy. If the photon got this energy, that means the electron had to lose that exact same amount of energy. So now the key is the electron lost it with the negative number versus the positive number, conservation. Like you remember Hess's law in chemistry, delta H is equal to negative Q. One goes up, the other's got to go down. That's why there's negatives here, right? The water gains energy, the chemical reaction loses it. Negative to positive. So this is the same thing. Photon gets the energy, electron loses it. Now, if you include this number in our calculation down here, final minus initial, you actually get the right answer. It works out nicely because that's a negative there already. Or you could just use your common sense and knowledge now and thinking, okay, this has got to go up. I've got to increase my energy. I'll just add this number to it. And I'm going to get somewhere in like the negative 3s range. Well, let's actually figure out exactly what it is here. We're negative 2.11 electron volts. My final, because it went down there, is that negative 5.14 electron volt number. I'm trying to find this initial, which happens to be M in this case. I'll just put M there. Okay, this is L. Okay. So I'm going to move this over to this side because I want that to be positive. I want a positive EM, right? There's a negative in front of it right now, so it's just easier to move it to the other side. And in the same time, you might as well just move this over there. So there's a little swap here. So we've got negative 5.14 electron volts. Oh, but to move it over, this negative 2, I would add it over. Negative 3.03. It makes sense that would be the number. You notice there's a little negative here for you already. Okay, so just 3.03. So awesome. Seems to be working pretty good. Okay. Follows this logic that those numbers should be larger. And this is a larger number than negative 5. Negative 3 is closer to 0, moving towards the positive side. So this is actually a larger number, which makes sense. All right, this question, we've done this question before, but we did this question for alpha, not beta. So we're going to not do alpha, we're going to do the beta one. So make sure you have the right numbers here. So to figure out the energy of the photon, I have to figure out what's the energy of the transition of the electron. This is my electron. So I'm going to go final minus initial, negative 89.2 volts minus my initial negative 9.4. Minus minus ends up being like a plus here, but you still get negative, but the negative makes sense. Makes sense in the question here, because this is my electron, and he is losing this energy. If my electron loses the energy, somebody's got to gain it. And the photon is going to gain it. Not going to lose that as heat, because there's nothing else to hit. There's nothing else to jiggle to cause any motion to. So there's no energy loss due to heat. So the energy's got to go somewhere and just into existence, a photon, off it goes. Right? Kind of strange. The photon didn't exist before, but now it does. Right? It has that same energy. And using that and the HF formula, I should be able to calculate this frequency. 1.9, I think 3 CDs? All those numbers have 3 CDs. Bada boom, bada bing, we're done. Perfect. That's high frequency. That's a nice number. You can actually calculate the wavelength if you want to figure out what this is. It's probably, what did I say, X-rays before. It's probably in the X-ray range at this point. It has a higher energy than the last one, so it's got to be a little bit further over. And the last one is like 18 nanometers. Now this is probably like 10 nanometers. You can figure it out. I'm not too concerned. There we go. All right. So stay tuned for the next video, and I'll see you then. Ho, ho, ho.